So welcome to 331, lecture 22. What I want to do today is I want to continue with one of the more interesting concepts in problem solving, monovariants. So we saw this briefly early in the semester when we looked at the rectangle or the chocolate bar game. What I want to do today is show that it can be used for a lot more, including some research I've done with students. So one of the points I want to do as we get towards the end of the semester is I want to talk to you a little bit about the small summer research program. If you're considering a career in mathematics or an allied field and you want some research experience, small is a great thing to do. And I want to show you a little bit about what I have done with some of my students. There is also a challenge problem, which if you can solve constructively, I will give you $500. If that's not enough money, I will give you $1,000. Yes, I realize this is bad negotiating practice. Really want a solution to this problem. Okay, so you should hopefully remember what a monovariant is. We're going to see some applications and some research. So an invariant, just for people who are watching this video who haven't seen the earlier lecture, is something that's constant in time. If anybody doing advanced physics here, if you were, this would be a great way to segue into Emily Noether's invariance theorems and whatnot. But since no one is, we will not. Monovariant is a quantity that can change only in one direction. When I've asked you in the past, people have correctly identified height is not a monovariant. That can go up and down. Weight can go up and down. Sadly, we believe age is a monovariant and only goes up. Okay. There's a lot of really good monovariant problems at this link. The slides will be posted online on the course webpage. If you want to try your hand at some really good challenge problems, there's a bunch of things at a variety of different levels here. There is a huge, huge advantage you have in trying to do these problems. Namely, I'm telling you, go to this link for a good set of problems involving monovariants. It's telling you, try to use monovariants for these problems. But again, when you're trying to problem solve, think baby crying. And when you're a newborn parent, you don't know why the baby is crying, so you just go through a list of things. Eventually, you start to recognize the different types of crying. It's the same way with problem-solving techniques. This is just something you should always be looking for. If you are doing differentiation, whenever you hear the word of, you should be thinking chain rule. Cosine of, okay, that of means it's going to be a chain rule. You can tell sometimes when it's going to be an induction. You can tell sometimes when it's going to be a monovariant. The difficulty is which monovariant. That's going to be a lot harder to find. All right, so I'm going to talk about zombies. And so there's lots of different zombie games you can do. I will start with the standard, and I will leave some interesting generalizations and open problems. So if you share walls with two or more infected zombies, and we're going to do things on a checkerboard, then you become infected. And once you are a zombie, you are always a zombie. Okay? So for example, let's imagine the following beautifully drawn configuration. And we have three cells that are zombies. The bottom row will be row 1, 2, 3, and row 4 on the top. Columns will be 1 on the far left, 4 on the far right. What happens in the next unit of time? Does anyone else get infected? So who gets infected? Yes. Which row? Fourth row, first, second, or fourth? Second column, yes. Third row, third column. Anybody else? So those are the only two that are infected. Since this is a 300 level class, I will assume that you can all quickly figure out we get 2 more infected at the next stage. And then when you look at this, 2 more get infected in the next stage. And what's nice now is while a majority of the land has now been occupied by the zombies, we do have some safe space. And so the question is, for a given configuration of zombies, will they eventually take over the entire country, or will there be safe spots? So whenever you do a problem, step 1 is to be a smartass. Just trying to, there's no substitute in the bottom. There you go. So step 1 is to be a smartass. Can someone give me a configuration, the easiest one you can think of cells to be infected with zombies that will guarantee that at some point in time, everybody's infected? The simplest configuration you can think of. No, that is not the simplest you can think of. Yes, all of them. If everybody's infected initially, do you agree that at some point in time, everyone will be infected? That's the easiest configuration. Okay, now what's a slightly easier one? checkerboard. Now you could actually do a little bit better than checkerboard. I could do everything but one cell. But checkerboard is still good. It's a 50% reduction in the cost of zombies. So, if I'm trying to have my zombie army, take over, this is a 50% savings. Now let's try to think on an n by n board, there's n squared spots. This checkerboard pattern is still going to cost me on the order of n squared. Can we do less? Can we do n to the 3 halves? Can we do n log n? Can we do order n? What's the best we can do? Anybody have any thoughts on the fewest number of initial infections that we need to get everybody? On an n by n. Any thoughts? What might be a good configuration? Maybe diagonal. It's not a bad thing to try, right? And the beautiful, Microsoft Paint animation, if we just keep going through, every moment in time, we get another diagonal above and another diagonal below, and we can see that the zombie infection will spread and we'll get everybody. So this proves that we can go from a quadratic algorithm, n squared, to a linear cost, order n. Can we do better? And by better, I don't mean maybe square root of n. I mean, can we at least get to n minus 1? So is it possible, if we have only n minus 1 cells infected, that at some point in time, everyone is infected? And so how should we attack this problem? What should we do first? I've got a deliberately blank page to force me to stop and ask you. What should be your first thought to try to analyze this problem? Good, but not a 2x2 board. There's something easier than a 2x2 board. 1 by 1. So we start with the 1 by 1 board, and we see clearly that with just n minus 1 infected cells, i.e. 0 infected cells, it's not going to work. On the 2 by 2 board, by symmetry, there's only one place to infect. And so we see that on the 2 by 2 board, it won't work. It's possible that maybe these are just small values and they're misleading. So we could look at the 3 by 3. And we analyzed, I believe, tic-tac-toe earlier in the semester, right? It was not a coincidence. This was foreshadowing, the art of a professor who's actually planning ahead. It may not look like that, but I wanted that done so that now for this lecture, I could say there's really only 3 initial moves by symmetry. And for those initial moves, how many responses are there? And so for the 3 by 3, I only have to choose 2 cells to be infected. So worst case, there's 12 things to check, but of course, a lot of them are going to be similar. If I start off with something infected in the upper left and then I infect the center, I don't have to worry about infecting the upper left and the border with the center. So I can really cut down on the number of possibilities. I'm not going to do the calculation. I'm going to just say that when you check all the cases, there's no way to have everybody infected on the 3 by 3 with just 2. Do you feel confident now to conjecture that you can't do it with n minus 1? Do you want more data? Okay, so I've just done up to 2024 in my head, and none of them work. I did every single possible configuration of infections of n minus 1 on the first 2024 boards. How many of you are Doctor Who fans? All right. So I wrote some really efficient computer code and checked all the way up to 2024, all possible configurations. Are you confident now? More confident is a good answer. I'm more confident now. The question is, if there's going to be new behavior, when should it emerge? I have a paper with Professor Goldmacher where we're trying to determine a limiting probability distribution. And the first 7 moments agree with the first seven moments of the semicircular distribution. And then the 8th moment differs. And it's not until the 8th moment that you have enough freedom for something to emerge. So sometimes you really want to get a sense of how far do you have to go. So let's try to look at what's happening and try to find a good monovariant. It shouldn't be surprising that we're looking for monovariant in a lecture on monovariants. And the monovariant, and this is where it's more almost art, it's difficult to think of what should be studied. What we're going to study here is the perimeter of the infection. So I don't care about interior walls between two infected cells. I only care about walls exposed to the rest of the world. Okay? So over here, imagine I have two cells infected in red, and then I have a cell in white between them that's now going to be infected. Okay? I only care about external walls. I know that the two cells above and below the white cell aren't infected, or would have had more infected neighbors. It only has two infected neighbors. So this white cell that's going to be infected, initially, two of those walls are part of the infection as exterior walls. And after it's infected, how many of the new infected cells' walls are exterior walls? 2. Has there been any change in the number of exterior infected walls? No, I started with 2, I ended with 2. The perimeter of the infection is unchanged. If I take the configuration of, say, west and north infecting my cell, I have 2 exterior walls, and then after the infection, I have 2 exterior walls. The perimeter is unchanged. I assume by symmetry, everybody is fine. I don't have to do north and east, east and south. What should I do next? I did east-west. I did northwest. What should I do now? North-south is going to be the same as east-west. Just rotate. So what should I look at now? I've done east-west. I've done northwest. How else could I have a cell become infected? I want to look at all possible configurations. I could have more than 2. This is all the ways up to symmetry of having exactly 2 neighbors infected. What should I look at next? 3. And so I chose to do north, east, and west. And so when you look at it that way, the exterior perimeter was 3 initially. Now it's 1. The perimeter has dropped by 2. And the only thing that's left is every neighbor is infected, and the perimeter goes down by 4. So the perimeter of the infection is a monovariant. It never goes up. It sometimes stays the same, it sometimes goes down. So the genius is figuring out that this is what you should study. Once I tell you that you should study this, it's not that hard to follow what I'm doing. But the hard part is coming up with looking at this. There will be no other class I think you take at Williams where we can spend this much time talking about how we come up with what to look at. And so this is just something to add to your arsenal of how do you attack mathematics. So now let's use this to prove the problem. If n-1 squares are initially infected, the maximum exterior perimeter would be if they share no walls. So the maximum perimeter is 4 times n-1 or 4n-4. If everybody's infected, what's the exterior perimeter? So you're on an n by n square. If everybody's infected, what's the perimeter of the infection? 4n. And I just told you if n-1 are infected, the maximum perimeter we can have is 4n-4, and the perimeter of the infection never goes up. So as time increases, the perimeter never increases. The perimeter of the n by n square is 4n, so at least 1 square is safe. So here's a nice proof. No matter what configuration you try, it's not going to work. Now, this is where things get really interesting. A lot of times in mathematics, I'll call it almost like a foothold approach. When you just get a little crack in, you can then exploit it even further. We just proved there's at least 1 square that's safe. Do you believe that there's only 1 safe square? Is it possible that there's only 1 safe square?
No.
Why not?
Because 1 square has either 2 or 3 or 4 neighbors.
Good. Right. So no matter what square you are, you have to have at least 2 neighbors, so you have to be infected. So our proof tells us initially that there has to be 1 safe square, but we now get for free there have to be at least 2 safe squares. So my challenge for you is, can you prove that it must be at least a safe what? Row or column, right? Up to, because I can always, so must there always be a safe row or column? We saw that in the initial configuration where we had 3 infected on the 4x4. We saw there was a row and a column that was safe. How far can you push this? And again, if you look at what we did, that was actually the maximum possible infection was the 4n minus 4. Could we get something that big? No, we're not going to get something as big as 4n minus 4. What can you do? And so, what kind of cells will you have to share and everything? So I'll leave that to you to see, can you prove that there has to be at least one row or one column that's safe? And then the last thing is, whenever you see something in mathematics, you should always ask about how you could generalize. So any thoughts about how you could generalize this? Almost anything you say is fine. How could we generalize this?
Seems like, I'm not sure if this should generalize, but it seems like the only stable configuration for infection is rectangular. Like it always
Okay.
So,
that seems reasonable that you should be able to prove that the final infection is always going to be a rectangle or union of rectangles. Yeah. That if you have a corner somewhere, something is going to be wrong. And if you have something sticking out, I don't think there's any way to have it sticking out. But how could you generalize the problem? That's an observation about the result, which is a nice observation. But how could you generalize this problem? What's a related problem you could study? Okay, and we'll do that in a moment. That's not quite the same as this, but what's a related zombie problem? If you want, I can really prime you for the answer.
If you're infected, not with 2 cells, but 1 cell.
Okay, so you could change how many cells are required to infect you, and how does that change the game? What if 1 cell is enough? Well, if 1 cell is enough, then what's going to happen? You only need 1 square. So we see that if it's just 1 cell, it becomes trivial. What if 3 cells are needed? What would the game look like then? Clearly, this will include that case. So we know that 3 cells requiring can't get everybody infected because 2 doesn't. So that's one thing you can do, is you can change the infection. What else could you do? Good, you could change the dimensionality. What if we're playing this on a cube? And now you have to have a certain number of cells around you. So one thing is to change the dimension. Another, if you want to say on the plane, is what if we did it on a hexagonal lattice rather than a square lattice? So whenever you see a math problem, you always want to ask, what can I do next with this? So the bridge problem we had, where I wrote the code and said it was around, I think, 16 and a half deals. This is the generalized coupon problem. I looked it up with some colleagues. There's a lot of literature on the limiting behavior of how long it will take, but it doesn't seem like anybody's looked at the related question of, if I want everybody to have seen all the cards, not just one player, how long do I expect to wait? Because now you have these terrible dependencies. And so it's really easy to find new problems. Whether or not you can solve those problems is different, but you want to just get used to asking questions. I may send you a document or a link from a Google Illuminate that a student did with a paper I wrote with another student. He wanted to test how well Google does at creating podcasts. It does a phenomenal job with the host. The person who's responding is good, but not as good as the host, because it's really easy to be a good host. Wow, that's really interesting. Can you say a little bit more about the techniques? There's so many just generic phrases you can use as the host. It's not hard to write the code to generate an AI host. To generate an AI response is a lot harder. And it wasn't terrible. And so you should just have a bunch of go-to questions whenever you see a problem. Let me change the dimension. Let me change the rules of the game. Let me change the board configuration. All right, so the next is Conway soldiers. This is one of my favorite problems. I was fortunate enough to know Conway when I was in grad school. If there is time afterwards, I will share some stories about him. Very generous mathematician with his time. He was always in the common room, always available to talk to people about math. Absolutely loved it. You could give him anything and he would find interesting, fascinating mathematics. And you could do an entire semester on just his strange observations throughout life. Okay, and that word was deliberately chosen for those who know his work. All right, so his problem is the following. Imagine you have an infinite checkerboard, and so I will draw the pieces from row 0 downward. Everything is filled with a checker. And checkers can jump either horizontally or vertically, and when you jump over a piece, the piece you jump over is removed. Here is the canonical way to move a checker up to row 1. Everybody agree that this was not that challenging? Can anybody give me a way to get a checker up to row 2? And again, without loss of generality, this has to be your first move. Is it possible to get a checker up to row 2? What could we do?
Not with the first one.
Not with the first move, but with some finite number of moves, can you get a checker up to row 2? Yeah. Good. Good. Perfect. So, whoops. So we have a series of configurations. I think I moved things towards the right rather than to the left. It doesn't really matter. And so we can easily move something up to the second row. There's other ways to do this as well. Here's another way of getting something up to the second row. Can you do something up to the third row, up to the fourth row, up to the fifth row? We've had success in getting something up to the second row. Do you think we can get something up to the third row? If you really worked on it, do you think you could do it? Yes, and the answer is correct. I have faith in you, and I believe you could eventually find it. What about fourth row? Do you think you can do it? I have faith in you. It's going to take you a little bit longer, I think, but I do have faith in you. What about row 5? Do you think you can get something up to the fifth row? You think so?
As long as you can have something on both 4 and 5, as long as you can reduce it to 4 and 5.
So you can get up to row 3 and you can get up to row 4. So, but it depends on how you get something up to row 4 as to, can you get something close to it? And so in the interest of time, I put this on, what is it, Amazon Turk, and had 1,000 people try for 1,000 hours, and no one was able to get up to row 5. Less confident now, I assume. What do you think we're going to need to study this problem? What do you think we're going to introduce? A monovariant, right? This is the lecture on monovariants, right? So the question is, what is the monovariant for this problem? So in some sense, a natural monovariant is going to be maybe some kind of weight or value attached to the board. And as I do moves, the value of the board is going to change. And I want to see if there's enough value here to move something up to row 3, row 4, row 5. So I hope this seems like a natural monovariant. And so what I'm going to do is I'm going to put something in row 5 as the target t. And I'm going to assign a value of 1 to that. And then I'm going to use, I hate New York City. I'll root for the Dodgers over the Yankees. I'd much prefer the media strike. But I will root for the Dodgers. Manhattan does have one advantage over Boston: the beautiful grid system. There's a nice, comedian who has a routine about what's the movie, Home Alone 2, where the kid is lost in New York. He goes, "How can you be lost in New York? You're at this intersection. You want to get to this intersection. Oh, you go this far over east and this far up north." It's a grid. So we're going to measure the distance from the target by grid movements. You can only move east-west, you can only move north-south, and it's the fewest steps needed. So if it takes you 4 steps, the weight is going to be x to the 4th. If it takes you 8 steps, it's going to be x to the 8th. So everything directly touching t is going to have an x. Everything touching something directly touching is going to be an x squared, and so on and so on. And so as you go further and further down, you're going to get a higher and higher power of x. Do you think x should be greater than 1, less than 1, or equal to 1? You're going to be assigning a weight to all the pieces, all the occupied squares. Do you want x to be greater than 1, less than 1, or equal to 1? So what would happen? What would the weight of the board be if x was greater than 1 of all the occupied cells? Positive what? If x is greater than 1, what's the weight here is going to be x to the 5th, x to the 6th, x to the 7th, x to the 8th. What's the weight of the 0th row going to be if x is greater than 1? So give me a number greater than 1. 2. All right, so if 2, what's the weight of this piece going to be directly under the x to the 4th? Not 16, 32. Because it's one more unit lower, right? So this would have a weight of 32. What would its two neighbors be? $64. So they're right, so they would sum to 128. And then 256, 512, 1024, 2048. What would be the sum of the weights of the first row? It's an infinite checkerboard matrix. So what would be the weight of that 0th row? It would be infinity. What would be the weight of the next row? Another infinity, and then another infinity. So the entire board would have infinite weight. So if I'm trying to look and see what happens, if x is greater than 1, I'm assigning an infinite value to the initial board. I'm never going to be able to get any kind of contradiction because the weight's always going to be infinity. Similarly, if the weight is 1, I'm always going to get infinity. So the only hope I have is maybe if the weight is sufficiently small, when I take higher and higher powers, maybe I'll get something that's finite. So let's try to calculate what the weight should be. So for the 0th row, we have an x to the 5th, 2x to the 6th, 2x to the 7th, 2x to the 8th. It's basically a geometric series. The only difference between this and the geometric series you're used to is that we are starting at x to the 6th. Well, that's okay. We know how to solve the geometric series formula. And so does everyone agree that this 1 plus x times x to the 5th over 1 minus x is the value assigned to the 0th row? Now we have to figure out what's the value assigned to the negative first row, negative second row, negative third row, and so on. If this is the value of the 0th row, how is that related to the value of the negative first row? Is there a nice formula? If you know the value of the 0th row, what would the value of the negative first row be? Looking at the picture. How do I get, if this was an x to the 5th, what's the value beneath it? If this was an x to the 6th, what's the value beneath it? So how do you get from a 0th row to the entry right below it? Multiply by x. So what's going to be the value of the negative first row? It's just going to be the 0th row times x. And what about the negative second row? What will that be? I'm sorry? Negative first row times x, or the 0th row times x squared. And so what we see is each row is just x times the previous, so we get another geometric series. And so the weight of the board is just going to be 1 plus x times x to the 5th over 1 minus x squared. As long as x is not 1, as long as x is less than 1, this is going to be a finite sum. Yes?
Why are we trying to calculate the weight?
Well, we're trying to find a good monovariant. And so I want to assign some kind of weight to the board, and then as I move my checker pieces as I jump, it's going to change the value of the board. And I want to then see if there's a piece at the target, that's going to get a value of 1. If the total value of the board is 1 or less, then there's no way I can move a piece up to 1 if the weight is staying the same or going down. So that's the idea, is we're trying to find a monovariant that will show that if there's a piece at 1, there's not enough value to get up there. And so there are two types of moves. We have, two pieces are in play, one jumps over the other, so you remove two pieces and you get another piece. If that new piece is further from the target, then I replace two pieces that were closer with a piece that's further. Clearly, the value of the board has gone down because I've lost two pieces that were closer and got a piece that was further. The other possibility is when I lose two pieces, I could get a piece that's closer to the target. And so I did lose two pieces, but I now have a piece that's closer. So I have to look at that second case. So imagine I have x to the 6 jumps over x to the 5 and lands on x to the 4. So what's the change in value? It's x to the 4th minus x to the 5th minus x to the 6th. Pull out an x to the 4th, you get 1 minus x squared. So if I set 1 minus x squared equal to 0, then there's been no change in the value of the board. Does anybody recognize the 1 minus x squared? This is a very famous polynomial. If it helps, I'm the president of the Fibonacci Association. It's almost. So the recurrence relation for the Fibonacci's is x squared minus x minus 1. Just replace x with 1 over x. It's basically going to give you the reciprocal. So this is a very famous polynomial. And so if we try to solve this, I used x to the 4th, x to the 5th, and x to the 6th. If I used x to the n, it would be the same argument. And so when I solve this, I get x equals -1 plus or minus root 5 over 2. If we take the positive root, it's basically related to the golden mean. And now we have a monovariant. And so when we choose the initial value of the board, when x equals root 5 minus 1 over 2, we get the initial value of the board is 1. If I have a target at 0,4, the value of something at 0,4 is 0.618034. That's less than 1. It means it is possible that you could move a piece up to the 4th row. This doesn't tell you how. It just tells you it's possible. However, if you have a target at 0,5, the board's value is 1, the value of the piece there is 1. There's no way you can do that in finitely many moves. Because in finitely many moves, you would still have infinitely many pieces left, and that would have some positive value. So there is no way to play this game and get a piece up to 5 or 6. What's interesting is there's an infinite version of this game where you're allowed to do infinitely many moves simultaneously. And if you can do certain types of infinite moves simultaneously, you can get up to 5. Basically, imagine all the checkers in the negative odd rows jump over all the checkers in the negative even rows simultaneously. And you have like an infinite jump like that. If you're allowing yourself to do stuff like that, you can do it. And there's a link to a paper that explains how to do this. Okay. We've still got 15 minutes left, so I've got enough time to show you a little bit of research and then some applications of what can we do with these monovariants. So this is research I've done with students. So as I mentioned, I am president of the Fibonacci Association. There are many ways you can write the Fibonacci numbers. We're used to the 1, 2, 3, 5. Each one is the sum of the previous two. The reason I don't like to start off with 1, 1 or 0, 1 is this beautiful theorem due to Zeckendorf. Every number can be written uniquely as a sum of non-consecutive Fibonacci numbers. So 222, this is using the greedy algorithm. At every moment in time, throw away the largest Fibonacci number you can, look at what's left over, throw away the largest Fibonacci number you can, keep going. It's a nice exercise to make this rigorous, prove this by induction. There's other ways to prove this which give a lot more information. If whenever you were doing this, you ever had two Fibonacci numbers that were consecutive, that would violate that at each moment in time, you threw away the largest Fibonacci number you could. So it's a nice exercise to make this rigorous. There are longer, more painful proofs, but they give you a lot more information. It turns out this is an equivalent way to define the Fibonacci's. They are the unique sequence such that no number can be written as the sum of two consecutive elements. As the sum of involving two consecutive elements. So if I start off with the number 1, I can't form 2, so I have to add 2. I can't form 3 by using non-consecutive elements, so I have to add 3. I can form 4 as 1 plus 3. I can't add 5, so I have to add 5. 6 is 5 plus 1. I can't do 7. I can do 7, 5 plus 2. I can't do 8, so I have to add 8. It turns out that this is equivalent. So there's this nice interplay between decompositions and recurrence relations. You're used to decomposing things in base 10, but you can actually work in Fibonacci bases. Okay. It turns out that the Fibonaccis have an interesting property. If you look at the decomposition using non-adjacent terms, the Zeckendorf decomposition, there's no decomposition that uses fewer Fibonacci numbers. There may be something that uses the same number. So if I give you 16, how can you decompose 16 as the sum of Fibonaccis? (13 plus 3), or you could do it as 8 plus 8. And so 8 plus 8 would not be a Zeckendorf decomposition. So I'm not saying the Zeckendorf decomposition has fewer summons than anything. I'm just saying nothing has fewer summons than the Zeckendorf. And you can prove that the Zeckendorf decomposition is summand minimal. There were some professors I was mentoring, and I gave them this question: what other occurrences are summand minimal? And unfortunately, they were too busy to work on it. So I then gave it to some students, and the students came up with the theorem as to when I use summand minimal. So I'm not going to go into too much detail in the interest of time. I will just say that there is a monovariant that you can associate. And we'll just focus on the Fibonacci case. And so if I have some decomposition, let's say I have AK copies of the kth Fibonacci, I can define what I'll call the index to be the sum of the copies times the square root of k. It's more natural not to take the square root of k, but just to do k. If I do k, it's not a strictly decreasing sequence. If I do square root of k, it's strictly decreasing, and it makes the arguments a little bit easier. So you have this horrible decision you have to make. Do I want to make the argument easier for me to write, or a little bit easier for people to read and understand? It's a little bit easier to do square root of k. It's not a big deal, though, to do either one. And so the key idea is, if I give you a number n and I want to look at its decomposition as a sum of Fibonacci's, well, clearly, I'm not going to use any more than the nth Fibonacci number, because I can't use a number bigger than it. And I can't use more than n copies of any number, because the smallest Fibonacci number is 1. So there's only a bounded number of possible decompositions for given n. That's really nice. So it means that there's only finitely many configurations to check. I just have to show that nothing has fewer summons than the Zeckendorf. And so what I'm going to do is show that the index is a monovariant. And I'm going to show that it ends in the Zeckendorf decomposition, and that as I go from any decomposition to the Zeckendorf, I never increase the number of summons. So if it's not the Zeckendorf, I either have to have twice of a Fibonacci, or I have to have 2 adjacent Fibonaccis. Because again, I can't have anything doubled, I can't have anything adjacent. And then all you do is you see, well, what would happen if I had 2 adjacent? I have root k plus 1 versus root k plus 2. And you just show that the left-hand side is greater than the right-hand side. That's why you want to use the square root. And then similarly, if I have something that's doubled, you just go through all the different cases. You have to be a little bit careful with 1 and 2 to show that it's always going to be smaller. And when you do this, you show that no matter what decomposition you're in, if you have something that's doubled or 2 things that are next to each other, you can get a smaller index by doing one of these moves. There's only finitely many decompositions. There's only finitely many possible values for indices. So every time I do this, I get something smaller, I get something small, I get something small. I can't do this infinitely often. So eventually I have to reach a point where I can't do anything further. What's the only time I can't do anything further? I don't have anything doubled, I don't have anything next to each other. This process has to terminate in the Zeckendorf decomposition. And because as I move, I've never increased the number of summons, the first move decreases the number of summons by 1, the second move keeps the number of summons the same. Nothing has fewer summons than the Zeckendorf. So this is a really nice proof that you can't have fewer summons than the Zeckendorf. In some sense, it's a really efficient way of doing things. It's a really nice application of monovariants. All right. I'm not going to go through the results that my students proved. It was really impressive. They came up with a really nice classification of when do you have an associated linear recurrence that has a minimal generalization of the Zeckendorf. I want to spend the last few minutes with games. You solve this $500, $1,000, I don't care. I want the solution. Okay, I came up with this game a few years ago when my daughter was young, and I gave it to one of my thesis students, and her thesis was, tell me how to beat my daughter. And just because this is being good, to beat her mathematically in a game. And she was able to prove something completely unsatisfying. She was able to prove that player 2 has a winning strategy, but it's a non-constructive proof. Non-constructive proofs are nice to know that the answer exists, but if you actually want to implement, a non-constructive proof is not good. So here's the game. It's 2 players. Whoever moves last wins, and you alternate turns. And we start off with the Fibonacci numbers, and we start off with n chips, and we put them all on F1, and everything else is empty. And then on your turn, if something is doubled, you can take those 2 chips and replace it with something 1 above and 2 below. And if you have 2 chips next to each other, you can remove them and put them 1 further. So it's the standard moves we talked about. 2 pieces on FK can become an FK plus 1 and an FK minus 2. You have to be a little bit careful if you have something doubled at 1. If you have something at FK and FK plus 1, you can remove and add 1 at FK plus 2. So does the game end? How long does it take? Who has the winning strategy for given n? What is the winning strategy? And so let's do a game. Let's start off with n chips at 1. The only move we have is we have to take 2 things at 1 and put them on 2. So now we have 8 things on 1, 1 thing on 2. And notice 8 times 1 plus 1 times 2 still adds up to 10. It's still a decomposition of 10. Now we have 2 possible moves. I could take 2 things at 2 things at 1 and put something at 2, or I could take a 1 and a 2 and put something at 3. Let's take 2 things at 1 and put them at a 2. So now I have 6, 2, 0. Okay, again, I have a couple of moves now. I could take 2 things at 1 and put something on 2. I could take 2 things at 2 and put something at 3 and 1, or I could take a 1 and a 2 and put something at 3. Let's take 2 things at 2 and put something at 3 and 1. So now I have 7, 0, 1. I notice it still sums to 10. I only have 1 move. I've got to take 2 things at 1 and put it at 2. And again, I have many possible moves now. I'll take something at 2 and 3 and put it at 4. I'm not going to go through the rest of the game. I'll just display all the moves here. And the column on the left in parentheses is just telling you whose move it is. So player 1 is moving. There's 10 things on the first bin. Next row, player 2 is moving. There's 8 things on the first bin, 1 thing on the second. And in this game, the game ends, player 1 moves and moves into the Zeckendorf decomposition. Player 2 has no moves, player 1 wins. When you look at this table, something should be a little strange. What do you notice when you look at this table? Something should look strange as to how things have been written.
Where is there space?
Yeah, why is there a space? On this move, player 2 took something on the first and the second and moved it to the third. If instead they took the doubled thing on the 2 and put something on the 1 and something on the 3, notice it now changes who wins. What this shows you, it is possible for different people to win depending on the strategy that's played. So unlike the rectangle game, which is really a sucky game because it doesn't matter what you do, a certain player is going to win. Or the triangle game, another sucky game, it's predetermined who's going to win. This game, it actually matters how you play. Both players can win. And so the question is, what is the winning strategy? You can prove all games end in a finite number of moves. It's basically just what we saw a few moments ago. You always end in the Zeckendorf decomposition. So all games will be finite. You can talk about upper bounds. You can talk about fastest games. You can talk about playing randomly and is it going to be a Gaussian? There's a lot of research projects. We have some results. I want to end today with a non-constructive proof that player 2 will always win as long as you don't start off with 2 chips. If you start off with 2 chips, the only thing you can do is you take 2 things on 1, put something on 2, and the game is over. Other than that, player 2 will always win, but it's non-constructive. Did we analyze the dot game before? All right, this is my favorite non-constructive game. So 2 players alternate. Whoever goes last loses. And on your turn, you choose a dot and you eat everything from that dot above and to the right. And so I'm going to prove to you that player 1 has a winning strategy. If it was whoever eats last wins, where should player 1 go if whoever eats last wins? So when you eat everything from that dot up and to the right. So if whoever moves last wins, where should player one go to win the game? Bottom left. Then you would win on one turn and the game is boring. That's why it's got to be whoever goes last loses. So imagine player one has the winning strategy. If so, they play it. If not, that means player two has the winning strategy. I'm going to show you how player one can steal. So player one goes in the upper right corner as a delaying tactic. Player two has a winning strategy by assumption. I don't know what it is. For definiteness, let's say it was eating this dot over here, and now we have all of these done. From this point onward, by assumption, player two has the winning strategy. That means whoever goes next is in a losing position. Player one says, I changed my mind. Take backsies. I didn't mean to go in the upper right. I meant to go where you're going. And that's my opening move. And we've now got the same position as a moment ago, but we've changed whose turn it is. So this is called a parity steal. This is an extremely powerful argument. Unfortunately, it involves needing to know where to go. And so there's lots of generalizations of this game that you can investigate. I'm going to just briefly show you that player two has a winning strategy. So the different levels are who moves. Top level, player one is moving, next level, player two, next level, player one. Let's assume that player one has a winning strategy. So we're going to color things in pink if player one has a winning strategy. So no matter where they move, it's still got to be a winning strategy. So when we go to here to one wedge two, player two is in a losing position, player one is in a winning position. The superscript is telling us just how many copies of each Fibonacci number we have. So in the bottom, we have n-7 copies of one copy of two, one copy of 5. Because player one has the winning strategy, it doesn't matter which way player two moves, player one is still going to have the winning strategy. So the next row, the third row, both have to be colored pink, and player one has a winning strategy from either of these positions. Let's look at what's going on from the one on the far left. Okay. That's the only place your player one can go from 1 n-3 wedge 3. So this has to be a winning strategy. So no matter where player two goes, it's got to be a winning position for one. And now if we look at the next one, this is where things get interesting. Imagine we move here. So player one moved to the top, then player two, player one, player two, player one. Over here, player two. It's the same configuration as the previous row, but we've changed whose turn it is. And so if by assumption, 1 to the n-5 wedge 5, we were calling that a win for player one. Whose turn was it? Player one, player two, player one, player two, player one. And so whoever's in this position, by assumption, has a winning position. That means this has to be a winning position now for player two, contradiction. And so you can then just chase things backwards. I'm not going to bother doing all of this. But you can then show from this that player two would be able to somehow steal the winning strategy. And you have to go through and analyze everything. The small games you do by brute force, once you get up to at least 10, we can use this tree. And there's a lot of related questions to this. I want to know what that winning strategy is. So I'm going to just quickly end by showing the slides with all the different, a subset of the students who've worked on this over the years, and then just putting up the references to, there's a lot of papers we've written. For people who are interested in potential small topics for the summer, these are very accessible. They're also extremely hard. And so frequently what happens is we find related problems to these that we can solve. These problems are too hard. But there's some new versions. I think I've just finished what we call the black hole Zeckendorf game, and I just got the drafts today, where once a piece goes beyond a certain Fibonacci number, it's removed from the board. And we have some new constructive strategies in those cases. All right, so this is a good place to stop. I'll eventually realize which one I should.